Good afternoon, everybody. It's such a pleasure to have Dr. Kanu Sinha with us today. She is an associate research scholar at the Department of Electrical and Computer Engineering at Princeton University. She earned a bachelor's degree from IIT, which is the Indian Institute of Technology. It's the MIT of India, if you've not heard of it. She has a PhD from the University of Maryland, and she's postdoced all over the world, including at the Institute for Quantum Optics and Quantum Information Science and the Army Research Lab. You should all know that she will be our neighbor very soon here. Sometime this spring, she'll be taking a faculty position at Arizona State University. In recent years, it's been really fun to watch Dr. Sinha's work. She's been developing all sorts of new ideas and concepts related to collective effects regarding atoms. And today she's going to be telling us a little bit about that as it relates to nanoscale quantum systems. So let's give Dr. Sinha a warm welcome.
Hi, everyone. And first of all, thank you so much, Ryan, for the very kind introduction and the invitation. I'm really happy for this opportunity to share with you all some of the ideas that we've been working on. So like advertised, I'll tell you guys about atom-photon interactions in nanoscale quantum optical systems and some ways to engineer them, okay? So let me first start with unpacking the title of this talk a little bit. And also, if there are any questions along the way, I'll be more than happy to take them as we go along. All right. So atoms and photons are the basic unit or quanta of light and matter. And in quantum optics, what we study is the various aspects of light matter interactions at the quantum scale, right? So interactions between single atoms and single photons are the basic building blocks of light matter interactions. And these interactions, of course, between atoms and photons also play a key role in several up and coming applications in quantum technology, as you might have heard. So for example, in physical implementations of quantum information applications, like building quantum computers, quantum communication systems and networks, in quantum metrology and sensing, building quantum devices like lasers, and so on. And while all these applications are super exciting and atom-photon interactions are really important, they're unfortunately also very inefficient. So one way to that you can think to boost these atom-photon interactions is to confine electromagnetic fields in smaller and smaller regions so that our atoms and photons can see each other better, if you will. Okay. And the other, so this kind of motivates us to shrink down our quantum systems towards nanoscales. And a more practical reason is that if you walk into a typical quantum optics lab, it looks something like this, where you have a jungle of big, bulky quantum optical elements that we would ideally like to shrink down to the size of a chip so that we can perhaps fit it in our pockets and use them more easily. And this brings us, therefore, to an emerging, or I should say already pretty emerged, family of nanoscale quantum optical systems that provide both very efficient as well as very tunable and engineerable light matter interactions. So here you can see a few representative examples of such systems. And, for example, atoms coupled to optical fibers that are few 100 nanometers thick, or atoms close to nanostructured surfaces like photonic crystals and atomic chips and so on. And what I've drawn here are some theorist cartoons, but of course these ideas are not just theoretical, they've very much been realized in labs all over the world. So here you can see some representative examples of these systems in reality. And in some cases, they've also been realized by the butterfly community. As you can see here, there's a nice photonic crystal structure in the wing of a morpho butterfly, which gives it the cool iridescent blue color that you can see here. And also, not only these ideas have been realized, but they are also being utilized for various applications like building single photon devices, sensing gravitational fields, building quantum computers, and so on. And to describe several of these interesting and exciting applications, particularly the quantum information related applications, one can make a generic schematic which kind of looks something like this. So here we have a bunch of atoms that are coupled to each other through waveguides or nanophotonic structures. And particularly in the context of quantum information applications, we think of atoms as the entities that hold the information. So they are the qubits, if you will. And the photons that travel through these waveguides are the vehicles of information from one qubit to another. And in such a scenario, there are two desirable features to have, among others. One is, of course, we'd like to be able to interface our atoms and photons more efficiently, so to build efficient light matter interfaces. And the other is to be able to connect multiple atoms over long distances. And these are the two broad ideas that I'll discuss today. Okay. All right, so let's start with the first one first, just to give you a very brief preview of what is to come. So one obvious way that you can think to enhance, to build, to enhance interaction between any two things, you would put them closer and closer together. And as we do so, as we bring our atoms closer and closer to, let's say, the surface of a waveguide, we run into fluctuation-induced phenomena. And what do I mean by that? So here, for example, is our quantum system of interest, which could be, let's say, collection of atoms or solid state emitters at a distance of few hundreds of nanometers from a surface of a waveguide or a resonator or photonic crystal. And as these two objects interact via the quantum fluctuations of the electromagnetic field, this interaction results in fluctuation-mediated forces, dissipation, meaning loss of energy from our system of interest, and loss of quantum coherence, which is an important resource for quantum information applications. Okay, so I'll first discuss some general ways to tailor and control these fluctuation-induced phenomena. And as a specific example, I'll talk about using collective effects between these multiple emitters in a collection of emitters to modify fluctuation forces. Okay. All right, and speaking of collective effects, the second idea that I want to discuss today is one of collective atom field interactions between distant atoms. So let me first define briefly what I mean by collective atom field interactions in quantum optics. So here, let's say what we have is two atomic dipoles that are radiating together in phase. So very much like two classical antenna, if you will. And the collective emission that comes out of this system as a whole, we know it can be enhanced as a result of a constructive interference between the fields emitted by the dipoles. And this is an effect that we know and love, and we refer to it as superradiance. And it's been known since 1954, as you can see. So breaking news, in other words. Right. And one common approximation that we make in studying collective effects or superradiance in quantum optics is that the atoms are confined in a region which is much smaller than the wavelength of the light that they're emitting. Okay, so what we'll consider here is that the atoms can be very far apart from each other. And what this brings into play is the retardation or the memory effects of the electromagnetic environment that the atoms are interacting with. So for example, here in the schematic, you can see there are two correlated or atoms prepared in a collective state at a long distance, coupled to each other through a waveguide. And as they each emit into the electromagnetic field of the waveguide, when the photons from one atom reach the other, there's an interesting effect from this delay or retardation, which causes them to emit in at a rate that is faster than regular superradiance. So this is something that we've been calling a super duper radiance, and that's the second idea that I want to talk about today. All right, so here's a brief outline of what is to come. I'll first give some background and introduction to fluctuation phenomena and talk about collective effects and fluctuation forces. And next, I'll talk about collective atom field interactions between distant atoms and the idea of super duper radiance. Okay, so in the first part, we'll be kind of shrinking things down, and the second part will be stretching things out, and that's the plan. All right, so let's start with some background on fluctuation forces. Fluctuation forces go by several names. So London, van der Waals, Casimir, Casimir-Polder, and they're all essentially the same thing. And I should mention that Ryan is an expert on fluctuation forces. So if you have any questions, I'm going to defer it to Ryan in the audience as well. The essential idea is this. So let's say we have two neutral bodies, A and B, that are separated by the vacuum electromagnetic field. And here is my vacuum cleaner. And as there's an interaction between light and matter, there are spontaneous fluctuations in the dipole moments that constitute the two bodies, as well as the electromagnetic field, which mediates an effective interaction between A and B, leading to a force. And depending on what's the shape, size, material properties of these objects and who originally happened to study them, we call these forces by different names. So for example, if it's 2 point-like particles, we call it London or van der Waals force. If it's a gecko climbing on a wall, we call it van der Waals. If it's two perfectly conducting parallel plates, we call it Casimir, and so on. So for the purposes of this talk today, I will be talking about particles or collections of particles near a surface, which we will refer to as Casimir-Polder forces or Casimir-Polder interactions more generally. Okay, now where do these forces become relevant as we shrink down our quantum optical system? So again, take all these big bulky optical elements and try to fit them on a chip. We run into atom surface interactions at nanoscales, right? And here, in such a scenario, these Casimir-Polder interactions influence how we trap our atoms, how our atoms decay, and how they decohere. So they're mostly a nuisance that we would like to control. And to kind of see how this happens heuristically, we can consider a toy model, something like this. So let's consider a dipole in front of a mirror. And we know from image theory considerations that the potential of this dipole has to scale as 1 over z cubed, okay? Where z is the distance between the dipole and the mirror. And this is not quite the right dimensions. So we know the only energy scale in the problem as far as the interaction between the atomic dipole and the vacuum goes is h bar gamma 0, where gamma 0 is the spontaneous emission rate of this atom. And so we plug that in the numerator, and this is still not quite the right dimensions. We need some length scale. And the only length scale that we know in the problem is the wavelength of the atomic transition. So we plug that in the denominator. And this is actually not that bad of an approximation. This is only a factor of 1/16 away from the actual Casimir-Poldru potential of an atom near a perfect conductor. And I can also explain that later if you're interested. All right, so if we plug in some typical numbers in this expression, we see that at distances of, let's say, tens of nanometers for a rubidium atom D2 transition, which is a very typical atom that's used in AMO experiments, there's a very strong attractive potential which overpowers our usual ways of trapping atoms using lasers and magnetic fields. Okay, so this motivates us to come with new ways to cope with fluctuation effects and to be able to trap our atoms and preserve their coherences, preserve coherences of our quantum systems at nanoscales. All right, so how can we do that? We can think of the bigger picture problem from an open quantum system perspective, which is something like this. So here, for example, we have our quantum system, which is open to interacting with an electromagnetic environment or an electromagnetic field bath. And the density of modes of this environment is modified in the presence of some boundary condition, okay? And as the system and the bath interact, there are all these interesting fluctuation phenomena that we'd like to be able to control. And in this schematic, we can see some ways that we can engineer these effects. So for example, we can think about modifying the density of modes of the bath by changing our surface geometry, its optical or material properties. We can think of changing the coupling directly between the system and the bath, for example, by using a magnetic interaction instead of an electric interaction. We can drive the system to some interesting non-equilibrium steady state, and we can use correlations internal to the system to kind of effectively change the system bath coupling. Okay, so this is by no means an exhaustive list of the number of things that one can do to tailor fluctuation phenomena, but these are some of the ways that we've poked at the problem of trying to engineer fluctuation effects in nanoscale quantum systems, and I'd be more than happy to chat about any of these ideas if you're interested afterwards. For the purposes of now, I would like to focus on one specific example, which is this idea of using collective effects to modify Casimir-Poldru forces. Excuse me. Okay, so like I mentioned before, collective effects have been known for some time, and the general idea is the following, where let's say we have, n atoms that are each independently radiating with a rate gamma 0. We can prepare these atoms in a super or a sub-radiant state, such that the emission can be either enhanced as a result of constructive interference or suppressed as a result of destructive interference. Okay, and you can ask, what if we take these interesting collective states and put them near a surface? And one thing, then we can kind of use this intuition that Casimir-Poldru forces are the dispersive counterpart of spontaneous emission or dissipation. And as a result, one might expect collective effects in Casimir-Poldru forces as well. And that's the intuition that we kind of start with. So here you can, guess already that the super radiant states, for example, will exhibit a stronger Casimir force, and the subradiant state will have a weaker Casimir force. And to kind of illustrate this more concretely, one can write a simple toy model of just two atoms. So let's say a red atom and a blue atom that are placed near a surface and interacting with the vacuum electromagnetic field. And we can again describe the interaction between the atoms in the field in an open quantum systems picture, where we can consider the atoms to be the system of interest and the electromagnetic field to be the bath with the density of modes modified by the boundary condition. And what we can do is we can effectively trace out the environment, which is something we can do in open quantum systems, to obtain the reduced, to obtain the effects of the environment on the atomic system, okay? So which is given in terms of this effective Hamiltonian. So if there are any theorists in the audience who wanted to see a Hamiltonian, here it is. And we can discuss what this means next. So what this Hamiltonian describes is all the effects of the electromagnetic field in the presence of the surface on the two atom system that we are looking at. And what are these different effects? So what we see here is that there's a shift to each of the excited states, a shift for each of the ground states, and some modification to the interaction between the two atomic dipoles in the presence of the surface, okay? And to kind of understand what these contribution looks like physically, you can think of processes where, let's say, an atom, which is in the ground state, emits a virtual photon and goes to the excited state and back. Such a process will yield some corrections to the ground state energy. And similarly, you can have an opposite process where an excited state atom jumps to the ground state and back, which yields a modification to the excited state. And what the states that we are specifically interested in are these collective states, which look something like this, where we have a superposition of the red atom and the blue atom, each being in the excited and the ground state. Okay, so in one case we have a correlated pair of atoms, and in the other case we have an anti-correlated pair of atoms. So to see what this looks like, again, the process for such a state will have additional contributions from the third term, which is the surface assisted dipole-dipole interactions. So you can see, for example, if we have a state where, let's say, there's a superposition of the blue atom being excited and the red atom being ground, with the blue atom being ground and the red atom being excited, they can exchange a photon via the surface. And in each of these two processes that you're seeing here and there, these processes can interfere either constructively or destructively with each other, depending on how the atoms are correlated. So this is the key idea behind there being collective Casimir-Poldr forces. Okay. All right, and we can look at this a bit more concretely in terms of some numbers. So here, well, these are, the expressions for Casimir-Poldr force on a super and a subradiant state. And schematically, you can see that it looks very similar to the super or subradiant spontaneous emission. And we can plot these forces for a system of, let's say, two emitters being close to a surface. And what we are seeing here is that as we, for example, put the emitters closer and closer to each other, there's an enhancement in the collective gamma, which is what we know from usual superradiance. And at the same time, there's an enhancement in the attraction, the Casimir attraction between, the atoms and the surface. And on the other hand, so you might think as a result that superradiant fluctuation forces can be useful for enhancing and sensing forces that are otherwise too weak to be measurable. And on the other hand, if we look at the subradiant state, we see that on the one hand, there is a suppression in the gamma or the spontaneous emission rate. And at the same time, there is a suppression of the total Casimir-Poldr force. And this is nice because what this suggests is that one can potentially use subradiant vacuum forces to build near surface atom traps by suppressing the undesirable attraction between particles and surfaces. And at the same time, having them live for longer because of the suppressed gamma as well. Okay, so to kind of summarize this part of my talk, I just want to reiterate that vacuum forces can be modified by preparing atoms in coherent collective states, and this effect can be understood in terms of interference in the surface-mediated resonant dipole-dipole interactions. And there are several applications to be explored with regard to sensing weak vacuum forces in the presence of with super radiant emitters, and possibly using subradiance to build for trapping particles near surfaces. Okay, and this actually, as we were writing this work, there was a very nice experiment in Maryland by some of my colleagues where they observed super radiance and subradiance in a system of atoms coupled to an optical nanofiber. So the experiment was very exciting to us at the time, because this is a collective system close to a surface, and it could be possible to potentially see some of these collective vacuum forces in such a system. It so happens that the center of mass of an atomic cloud is too delocalized to be able to see these forces in action. But as we were discussing this experiment, we got into a separate rabbit hole, which is what I'll get into now. So you can see the title of this paper, which suggests that, so one of the experiments that they did one of the results that they had in this paper was that they separated the atomic cloud into two subclouds. And what they observed was that the super radiant emission from the atomic cloud did not change. And that led them to conclude, that led the authors to conclude, the title of the paper, which is that super radiance shows that the dipole-dipole interactions mediated by the optical nanofiber are infinite ranged, as in you can separate them however long you like, and it would not change. So we kind of started questioning that, and this brings me to the second part of my talk now, which is collective interactions between distant atoms. So before I get into the actual system, I want to give a brief introduction to non-Markovian dynamics, because that's an important aspect of this problem. So one common approximation that we make in quantum optics is the Markov approximation. And what does that mean? So here, for example, we have our quantum system, which is interacting with a bath. And when making the Markov approximation, we assume that the correlations of the bath decay much faster compared to the rate of system relaxation, such that the system, as it evolves at every instant, it doesn't have any memory of its previous dynamics. Okay, so it's a bit of a forgetful system, if you will. All right, and now we can consider a schematic where we have a delocalized system. So we have subsystem 1 and subsystem 2 that are both coupled to a common bath and separated from each other by a distance d. And in this picture, we can make a couple of heuristic timescales. So we can say that there's a timescale associated with the bath correlations to travel from part of the system here to part of the system there, which is this d over v, where v, let's say, is the velocity of the bath excitations. And there's a relaxation rate of the system, gamma, which is, let's say, the spontaneous emission rate of the atoms in the waveguide. And if we are to apply the Markov approximation, what we are demanding then is that the ratio of these two timescales be much, much less than 1. Okay, and this dimensionless number is actually insightful in telling us different origins of non-Markovian behavior or scenarios where we can no longer forget the memory effects of the bath. So for example, you can see that if I have slow modes in the bath, meaning that the excitations of the environment will spend a lot of time lingering around the system and therefore carry memory effects, this will lead to non-Markovian behavior. And similarly, if we have strong interactions or strong coupling between the system and bath, that will also lead to memory effects. And what we'll discuss today is the effects of retardation in a delocalized system that brings into play non-Markovian effects. And I should also mention that some of these aspects of slow bath modes and strong coupling in the context of collective emission have been studied in some of these very interesting works and more, in fact, which I don't have here, but what we are looking into is the aspect of retardation. Okay, and where is this interesting? So of course, there are several motivations to coupling quantum emitters over long distances from the perspective of building quantum networks and doing distributed sensing and metrology protocols and so on. And not only these retardation effects are relevant in those systems, but it's been shown that such retardation or time delayed feedback can be useful for efficient generation of entanglement between distant emitters. So there are some works here where people have shown that these retardation-induced effects can create interesting photonic cluster states, interesting atom-photon bound states, and so on. Okay, so with that motivation, we can jump right in to a toy model which describes the system that we are interested in. So here, for example, we have again two level atoms that are each coupled to the waveguide in this case, and at a distance d from each other. And we assume that they're initially prepared in a super or subradiant state. Okay, and these atoms emit into the waveguide with some rate gamma 1d. We can describe the dynamics of the total system, assuming that they stay in a single excitation subspace, meaning that at most there's one excitation in each of the atoms or in the waveguide. Okay, and the dynamics of the system can then be described in terms of these very simple looking coupled delay differential equations, which you can see here. So the first term describes the spontaneous decay of the individual atoms into the waveguide, and the second term here describes how the other atom acts on the first with a bit of a delay. Okay, and you can see that there are some important factors here coming from how efficiently the atoms are coupled to the waveguide and what is the phase that the field acquires in its propagation from one atom to the other. And I wanted to mention that such delay coupled delay differential equation system or dynamics is pretty generic in all kinds of systems, ranging from instrument design to ADS-CFT correspondence and population dynamics. So you might equivalently be describing a system of quantum rabbits interacting with quantum foxes running through waveguides and looking at their population dynamics. So the nice thing is, though, it's a very well studied dynamical problem, and we can therefore look at what the dynamics actually is. So here is the result, which is the amplitudes of the two atoms as they evolve as a function of time. So what's going on here is you can see that there's a cascade of stimulated emission processes. So you can understand this as each atom emits a photon wave packet, it gets reflected back and forth between the atoms and modifies the atomic dynamics each time there is, there's a one-way trip of the photons, okay? And this kind of a mutually stimulated emission behavior can be best seen just after the one-way trip. So if I truncate my full solution, let's say, to right when the photon from one atom has reached the other, here the first term corresponds, of course, to the spontaneous emission, which we know very well, an exponential decay with time. In the second term, you can see that there is a modification now coming from the interaction of the first atomic dipole with the photon that comes from the second atom. And if we look at this second term a bit more closely, in particularly with regard to what is the instantaneous decay rate at the instant when the first atom sees the second and vice versa, we note that for a super radiant pair of atoms, this gamma effective can be can exceed 2 gamma, which is the super radiant gamma. And on the other hand, the subradiant state decay can be negative, meaning that there is information coming back from the environment into the system. And that's a very quintessential memory or non-Markovian effect. Okay, and we can look at these dynamics as in this picture, where what we are looking at is various time evolution for different distances between the atoms. So, for example, this blue solid curve that you see, this corresponds to the atoms being on top of each other. So that's just regular super radiance for a for 2 coincident emitters. The black dotted curve corresponds to the atoms being infinitely far apart. So they emit pretty much independently throughout. And somewhere in between, so for example, for a dimensionless distance that we defined before, for an eta value of, let's say, 0.5 or so, we see that there is, independent emission until the atoms see each other, and then they emit faster than 2 gamma. And that's better seen on this log-log plot. And this is what we call as super duper radiance. And I wanted to mention that the names ultra radiance and hyper radiance were taken by other people. So that's kind of what we're stuck with. And to see the dynamics from the perspective of the field, we can see here the the 2 atoms emitting into in a space-time diagram. So here what's going on is that the 2 atoms are located at these 2 points, and as they emit into their respective light cones, you can see the 2 light cones coming out from the atoms. When the field from one atom reaches the other, there's a strong enhancement outwards, and that's precisely the super duper radiance part. On the other hand, in the subradiant case, you can see that there is an interesting formation of a bound state in the continuum. So this, this is like a cavity, if you will, which is made by the atoms, for the atoms, and so on. So it's a pretty democratic cavity, if you will. Okay, and then so all this is fun and interesting, and you might ask, what is this good for? So in that regard, one can define a cooperativity parameter which is an important parameter when considering quantum information protocols. So what we thought is that if we have a faster decay for the instantaneous emission from the collection of atoms into the waveguide, maybe we can boost the overall cooperativity of the system. Unfortunately, that is not the case. So here, if we define a cooperativity parameter where let's say, which is the ratio of field, the total field emitted into the waveguide to the total field emitted outside of the waveguide. The cooperativity for a super radiant state, unfortunately, always reduces with delay. So this is, not great in the sense that we cannot boost our cooperativity with retardation effects, but nevertheless, it's an important factor to keep in consideration when doing quantum information protocols over long distances. And to get back to the question that we kind of started out with, how do these, what happens to dipole-dipole interactions when you take them, when you separate your dipoles infinitely far apart, or again, at a very, very long distance anyway, we can derive an effective Hamiltonian for this system in the presence of retardation. And this is what it looks like. Of course, it's a time-dependent Hamiltonian, being non-Markovian and all. And the effective dipole-dipole interaction in energy, we can see that at the instant where the atoms see each other, looks something like this. So here you can see that dipole-dipole interactions in 1D are not exactly infinite range. They do have an exponential dependence on the distance. And this contradicts what we assumed before. Okay, and to kind of, so I also wanted to share that we are currently looking into experimental systems to study some of these effects, both in a circuit QED platform as well as in a system of atoms coupled to optical nanofibers at Maryland and in Sweden. And I'm pretty excited about these experiments, and I'll be happy to discuss those in detail as well afterwards if you're interested. So just to kind of summarize what we've shown, what we've seen is that collective spontaneous emission can be modified as a result of delay and retardation effects, which can result in a counterintuitive enhancement of instantaneous spontaneous emission rate beyond Dicke superradiance. And also for the subradiant states, we find that there's an interesting bound state formations. And we also find that there are limits to dipole-dipole interactions and cooperativity in atomic systems in 1D. Okay, and this answers some questions, but opens many more, which we've been looking into since. So how does this affect scale with the number of atoms? This has been answered, for example, in some of these papers. How does the system behave in the presence of multiple excitations? What happens when you drive the system? How are these effects pertinent to actual quantum information applications? And for me personally, most exciting are the experimental demonstrations. So that's what we've been exploring since. Right, and with that, I would like to thank you all for your attention and thank my awesome collaborators on these works for their collaboration. I'm happy to take any questions.
Great, thank you so much, Kanu. We've got some questions. Jaime, do you want to come down here? I'm going to have the students actually come down and ask you. Hello, thank you so much for your talk. I'm a theorist, and so when you shared the Hamiltonian, I was really excited, so thank you for that.
Oh, perfect. So I have more slides for you, actually. Yeah,
so
I've got Princeton first.
But actually, this is actually a non-theorist question, because once you showed me the Hamiltonian, and I was thinking about how the interactions that you're talking about, the dipole-dipole interactions, I was really thinking, how would you do that experimentally? So
Now that you brought up the very end, I was wondering if you can go into a little bit more about what your ideas are for the experimental setup for measuring these interactions.
Okay, good question. So I do have a slide about experimental illustration somewhere down the line. Let's see, not this one. For some reason, I'm not able to see my future slides, but just hang on. Okay, yes, here. So one possible way to observe collective fluctuation forces could be to, for example, consider a system where we have a nano diamond embedded with emitters, solid state emitters, and we can put this object on a cantilever close to a surface. And if we plug in some, typical numbers, and let's say we start with exciting the system. If you're familiar with the Dickey ladder here, so I can excite my system all the way to here, to this level. And as it tumbles down, it goes through the super radiant state, which is this m equals 0 state, towards the ground state. And as that happens, we see that there's a boost, or rather a burst in the spontaneous emission case. On the other hand, in the force case, there's a boost in the force that we might be able to observe if we're measuring the force on this cantilever that's holding the particle. So if, let's say, you have 10 or 12 emitters that are acting cooperatively, this boost can be as large as tens of femtonewtons, which can be possibly measured in the lab. So does that answer your question?
Yeah.
Okay.
It's really exciting. Thank you so much.
Thanks.
Other questions? Yeah, Bertrand.
Hello, I am Bertrand here.
Hi.
Thank you for your talk. Just a question here. You were talking about atom interaction. I assume that some atoms are interacting more than others under certain conditions. Can you simplify a little bit? What kind of atom are you thinking about, and what kind of possibilities you see to eventually have stronger or weaker interactions going forward?
That's a great question. So here, well, one thing that I've assumed is it's a very sort of a generic atom field interaction without particularly specifying the couplings. And the couplings are implicitly there in the effective. So you can see the gammas that we, so here, for example, this gamma coefficient that you see is a result of interaction with the field and back. So this scales as the atom field coupling square. And the effective interaction between the two atoms coupled via the waveguide scales with that gamma and waveguide coupling efficiency beta, which depends on how close you are to the waveguide. And we are assuming that we are not in a strong coupling regime, as in certain approximations that we use rely on the fact that the atom field couplings are somewhat weak. But it's a very interesting question, what happens when one does go into strong coupling regimes, and there will be additional terms coming into this interaction, and they'll have more interesting physical effects, which we haven't explored here yet.
Great. Other questions? Yeah, John.
Hi, I'm John, and
Hey.
thanks for the talk. And I had a question about when you're talking about the collective effects when we bring those atoms near the surface. Is there a point where that starts to break down when you get too many atoms, or does it just continue? Yeah. At what point does that happen? It doesn't happen.
Very good question. So in the calculations that we've done, we were assuming that perturbation theory applies, meaning that the shifts that you get out of these interactions are not, of course, as strong as the atomic transition frequencies. So there will be a point where perturbation theory breaks, and that's when you would want to look at more exact descriptions of these effects.
Okay, thank you.
Sure.
Any other questions? I've got one for you, Kanu.
Yes, please.
You found a discrepancy between the interpretation that you have infinite dipolar interactions in a waveguide. You found that, in fact, it exponentially decays. Can you tell me how that can be reconciled with the work by Ralston?
Oh, you mean the infinite range thing?
Yes.
They are at very short distances. So the thing is, if you look at this factor, the eta, that's the distance divided by the coherence length of the photon. And coherence length of the photon is C over gamma, gamma being roughly 20 megahertz or so. That number is tens of meters. So if you go to 10 meter, which we are doing now, so that's what this experiment is doing. So here, now what we have in the lab is a system where you have the cloud and a couple to these 2 nanometer sections, 2 nanofiber sections. Thanks for that question, by the way. Now I get to talk about this experiment. And then you can excite this cloud from the side. So you'll have one delocalized excitation throughout that cloud. And then there's a very long, 10, 20, how many meters you want to have between these two. So when the atoms emit, we are hoping to see some interesting, retardation induced effects, but we haven't seen any yet. So I'll keep you posted though.
Yeah. Well, let's thank Kanu, Dr. Sinha one more time. And now we'll transition to the Q&A for the grad students, but I want to kick the faculty out first.
Okay.
So I check to see if we have any faculty that are still on, and I'll stop the recording.